So the first topic today, STL iterators. Recall the last tutorial, we introduced C++ templates and our STL standard template library, where you can reuse the templates that are written by other people. And we briefly covered the std vector as an example, and that's from the containers library. Today, we are going to start with iterators. Iterators are defined on any of the STL container library, and we'll be using the list as an example, and we're going to compare the list with the vector. What are iterators? Iterators are essentially pointers to elements in the container, but they're not really pointers. They're just made to look like pointers. So they can be pointing to an element in the container. It can be referenced and dereferenced. And it allows us to move between elements in the container. You might not see it coming from the vector class that we discussed last time because vector is already really efficient in accesses, but we'll be talking about more containers later. The iterator only defines operations that are efficient for the specific container that we're talking about. For vectors, why not we just use the array square bracket index to access the elements, but use iterators? And that's because vector container supports random access, and that's why we can use the operator square bracket. But operator square bracket only implies random access and is not defined for the containers that do not support random access, like vector. In the STL, all of the containers have iterators defined, so the iterator syntax can be reused across containers. The operator square bracket cannot. Each container has its own iterator class defined. And the syntax looks like this. Remember the classes, the containers are templated classes. So a vector of int is different from a vector of float. They're different classes. And the iterator classes under them are also different. std list also has iterators defined. They're all different classes. They're just called iterators, just to be consistent. And different iterators support different operations, and we'll see them coming. Let's still take the vector as an example. We can use the square bracket for accessing and modifying. We can insert using pushback. We can query with size, all of those with complexity 01. Adding on iterator functions, we have the begin function and the end function. They both returns an iterator either to the first element or the element that is one past the last element. So the end is actually not pointing to anything. It's pointing to, if it's a pointer, then it's a null pointer. So it's not pointing to anything. It points to a conceptual place like this. My vector.begin points to index 0. My vector.end points to one past the end of this vector. And this is only used for bound checking. It's pointing to empty space, and when we loop through it, we will loop from begin. We increment by 1, and we check if we're at my vector.end, we terminate right away. So Let's go over some example usages of iterators just to get the idea. Case 1, we're declaring a std vector int iterator object called it, and we are assigning that to numbers.begin. Can I get a show of hands? How many of you would think this is valid? How many of you would think this is not valid? Okay, this could be hard because this could be the first time you see something like this. So if you declare an iterator object and you assign numbers.begin to it, it's valid because numbers.begin is an iterator object. Now, case 2, it equals 5. How many of you would think this is valid? How many of you would think this is not valid? I see one hand, two hands. So both of you are correct. It equals 5 is not valid because it is an iterator object, so it's a class. 5 is an integer. You cannot assign any integer to a class object. So no. Case 3, it plus plus. Any of you think this is valid? 2 hands, 3 hands? This is valid. It plus plus will increment iterator to the next element. It minus minus. How many of you would think this is valid? I wish I could see more hands. It minus minus is similar to plus plus. It will decrement the iterator to the previous element. Int x equals star it. Any of you think this is valid? Any of you think this is not valid? 1 for valid, 0 for not valid. This is actually valid because iterators can be used like pointers in this case. So we are actually dereferencing this iterator and getting the value at that position and putting into X. So this is valid. Iterators should be dereferenced to be accessed. Case 6 and 7, they are really similar and they essentially can be used interchangeably in some cases. So, how many of you would think they are valid? 6 and 7. How many of you would think they are not valid? We have a 2 by 2. Both of them are valid in the vector case. So we can compare whether the iterator is numbers.end to check whether the current iterator is pointing to a valid element. If it's invalid, it's going to equal to numbers.end. And it's a similar logic for less than. We just need to be careful because for some containers, the less than operator might not be defined. But in most, they should be defined. So case 7 is valid in this case. The not equal to is always defined. So using case 6 is always safe. Number 8, case 8. How many of you will think this is valid? Wish I could see more hands. This is valid because we are assigning 27 to the dereferencing location of IT. We're modifying the element at IT. Case 9. Yep.
What's the difference between pointers and decorators again?
So pointers are integer types, essentially because they stores the actual location the memory is. It stores the address to the memory. But iterators, they are not. They are classes. So something like this, the dereferencing in iterators is implemented as an operator for the class. But for the pointers, dereferencing is just part of the concept of a pointer. And that's a difference. If you attempt to output the contents inside an iterator, you will get some really weird things. But if you attempt to output the contents of a pointer, you will get the actual memory address. So iterators are pointers for the container libraries only. And you won't need to care about the memory in any way for the iterators because all of them are handled by the library itself. Okay, back to case 9. How many of you would think case 9 is valid? So basically, we're doing iterator plus 2. How many of you would think this is not valid? 1 for not valid, 2 for not valid, 3 for not valid. We're actually in vectors, and this is actually valid just in this case. In many other cases, this might not be the case. But thank you for participating. It's really nice seeing the hands up. So then looping through a vector, there are 2 options. The first one is to use the indices like what we've been using. And the second option is to use iterators. We start from numbers.begin, the first iterator, and we loop through it until the end. And we output the dereferenced iterator. So because we're dealing with iterators, the syntax should be similar to dealing with the pointers to that element in that container. Yeah.
Would you say that it's supposed to be C++ iterators?
Complexity-wise, there's no difference between the indices and iterators. It's coding style-wise, using iterators can be beneficial in some cases. Using indices can have shorter code because you don't have to type that much things. But using iterators can allow you to switch from vectors to lists to other container types really easily because other containers might not have this indices defined. So everything's engineering choice. So yeah, declare the iterator type, initialize to the first element, ensure the iterator is valid, so it's not at the end. We advance to the next element after this loop iteration is finished. And we need to dereference to get the values. And now let's use something similar to this for loop and do an example. So this is a function that wants to extract negative numbers inside this vector of int. And we want to push them back into this empty negatives vector and return it at the end. We want to use iterators to loop over the integers and doing the pushbacks. Let's go to this URL and let's complete this exercise 1. you should arrive at something similar to this. So we are making a for loop. We make an iterator IT that starts at integers.begin. We check whether it's integers.end, and we increment it every iteration. Inside the for loop, we do dereferencing of IT. We check whether it's less than 0. If it is, then that's a negative value, so we push that back into negatives. And we need to remember dereferencing it because it's iterator. Now, this is an example of how to erase a certain value inside the vector. And we're using the remove negatives as an example. We're checking whether it is a negative number. If it is, then we erase it using integers.erase it. So the erase member function of vector will then erase whatever is pointing to by it, and it will return the iterator to the next element in the vector. And for that reason, we cannot do it++ in the for loop. We have to do it in else. Because if we do a erase, this it will already be pointing to the next element. So we need to it++ here in the else. What does erase? Yep.
It's also word. Like the word IT plus in the for loop, but then if statement gets executed, it can IT minus.
That will work, but there will be corner cases. You can think about this. So yeah, let's say if you're erasing the first element, right? If you erase the first element, it will point to what was at the second element. But then when you do it minus minus, you're doing one before the first element, which doesn't make sense, right? What does erase do for a vector? Because we're working with an array that's continuous in the memory, and we want to erase some negative number pointing to by it. What this will do is it will remove this one, and it will copy over all of the unprocessed elements here. And that's a sign of, yeah, and we are returning it2, pointing to this element, which is the next element to be processed. And that is sign of O(n) complexity, because we have to copy over many elements to the new vector. So erase itself has the complexity of O of n. Now let's think about what is complexity of the remove negatives function here. So we're doing a for loop that loops through the entire vector. And inside it, if it's a negative value, we call erase. And erase is O of n. What is the entire complexity of remove negatives? What is the total complexity? Yep, O of n squared. Because on average, if we do, like in the worst case where all of them are negative numbers, we're doing n times n. On average, it still can be half and half, and that's still on the order of O n times n, so n squared. We loop over n elements and we do O n each time in the worst case. On contrast, if we consider a linked list, so STD list is a doubly linked list. It can go to the next element and the previous element. If we need to insert and erase anything in between using iterators, the list can actually do it in one time, because the only thing it needs to do is to either create a new object or remove one object, and we just need to update the next and previous pointers. Nothing else. So that's O1. Comparing vector with list, the begin and operators, the begin and functions that are returning iterators are taking O1 pushback, takes O1 sides, takes O1. And the side function is only coming to support in this since C++11. If you happen to use an older C compiler, which I doubt, you will not see the sides function. But I think nowadays, all of the C++ compilers will support after C++11. Operator square bracket is one time in vector, not available in list because it implies random access. Linked lists are not random access containers. For erase and insert using iterators, so that means erase and insert into the middle of the container. For vector, we'll need to copy the tail part, either one previous or one afterwards, so it's ON. But for list, because we only need to update the neighbors, it's O1. Iterator type, for vector, it's called random access iterator, and it can do plus plus, minus minus, plus 5, or plus any number. For list, it's called bidirectional iterator that only can do plus plus, minus minus, but not plus 5. And there are also something that's called forward iterator that only can do plus plus, not minus minus, like a forward list. So when you're choosing which container you're using, just keep that in mind and only use those that have enough support that you need. For the remove negatives, lists will benefit more than vectors because list will only take ON in total. Erase will only take O1, and O1 times ON is ON. Vector takes ON squared. And if we need to change from vector to list, it's really easy if you're using the iterators, because the only thing you need to do is to search and replace vector with list. You don't need to modify anything else unless you're doing something like IT plus equal to something. If you're only doing plus plus minus minus, then you don't have to care about other things. So yeah, we can quickly switch from vector to list. The remove negatives is ON complexity. Just be careful, not all code works interchangeably with all containers. So if you're switching between containers, just make sure your code is still supported in the new container. Any questions till this point? Let's continue. The auto keyword. This is something that's being really widely abused. Just don't abuse it. The auto keyword is only there to help you save on typing. Like if you are doing something like std list int iterator, if you replace this entire thing with auto, this will still work. But just in case, you still need to know that it's a iterator from the list class. So this saves on typing and it keeps code compiling when you switch types around frequently, because then you don't have to manually switch from vector to list here. You only need to switch this one. Just be cautioned, you should always still know what the actual type will be, and this type, after the first assignment is made, this type is made static. So the compiler will still treat auto IT equals integers of begin. Compiler will treat it like this. This is not Python. The auto type does not mean the type can change dynamically. It will fix to the type after the first assignment is made. If that is clear, let's see it. So instead of typing std vector in the iterator IT, we just need to type auto IT. And these two lines can be then combined into one line. This will make your code shorter, which is a good thing. Simpler still, we can use the range-based for. The range-based for is defined for all of the containers defined in the SDL containers library. And the syntax looks like this: for auto reference item within this container numbers. What this does, the auto reference is a reference so we can change the values. So we can directly access the values because they are referenced. You no longer need to dereference the pointers, the iterators or anything. You directly access the item. Auto will automatically determine the type. In this case, we're accessing a vector of integers, so auto will be int. Colon numbers means we will loop from dot begin to dot end in the numbers container. This item variable will hold the reference of the item you are looking at in this iteration. So that's something useful that you can use. A really simple range-based for. If you have like specific ranges you need to look for, then probably a manual for would work. If you just want to search the entire container range-based for, is good for you. Because it saves on typing and you don't have to worry about dereferencing. All right. Let's do a demo. Hopefully my BNC is still there. Hey, where am I? So let's see what we have here. This demo is just to show the speed differences between vector and list in the erase negative example. So we just have two files in here. The list erase .cpp uses the list. Vector erase uses the vector. All of the numbers are the same. They perform the same things. Randomizing first, and then we do remove negatives. These are exactly the same code. The only difference is list versus vectors. All right. And we remember that erase negatives is O(n) squared time in the vectors case and O(n) time in the list case. Let me make clean and let me make with release configuration. And let me compare the times between them. First is the time that takes O(n) squared. Don't panic, it's just still running. That's O(n) squared. And that makes perfect sense of why we ask you not to use algorithms with O(n) squared complexity, because it will take 19.13 seconds in this case. That's time. Exactly the same operations, but O(n). 0.22 seconds. That's the comparison of the wall clock time between O(n) squared and O(n). And that's why when we're doing algorithms in general, we would ask for at least something that's less than O(n) log n. Just don't get to O(n) squared. It's going to be crazy if your n is big enough. If you only have a small n, then O(n) squared is fine. But if you're having an n that's big enough to dominate your calculations, make sure you have a more efficient algorithm to use. Good. So that's it for iterators, and let's move on to the next one. STL containers. You shouldn't be too foreign to this concept because we've been talking about STL containers all along. Vectors are STL containers, lists are STL containers. And now we're introducing associative containers. Vectors and lists are sequential containers that are essentially 1D. You can visualize it as either a chain or a 1D array. Associative containers are more widely used in a lot of the cases, and there are the unordered associative containers. We'll be covering them one by one. First, let's consider a really widely used case of finding a value inside a container. If we have a vector, option 1, we use the find function from the STL library. What the find function does is it goes from the begin iterator, it goes to the end iterator, and it searches linearly. It does a linear search and it stops whenever it finds the value that we're looking for. This is O(n) complexity. It's just a simple linear search. And if you are working with something like vector, there's nothing better than this. Option 2, sort the container and then search by something like binary search. But this requires the container to be sorted. It could be difficult, it could be error prone, and sorting the container itself takes at least O(n) log n. So you will need to perform more searches than you should to make up for that sort time. So So it's also not a really good option either. Better options, what data structures are there that can be inherently ordered? So we don't have to explicitly order them. We can just directly search by binary search. And now we're no longer thinking of containers that are 1D. You should already know one type at least that is inherently sorted or ordered. And when you search in it, it's O log n. There is one data structure that you should already have learned. Any idea? Yep. Binary search tree? Binary search tree. In the STL, the binary search tree is called STD map. STD map is a self-balancing binary search tree so that you don't have to worry about it being unbalanced and going into the worst cases. It guarantees O log n complexity for find, insert, and erase. STD map stores pairs. The first element in the pair is the key that the binary search tree is using to sort. The second value is the value that is stored at that node. One useful example is the domain name lookup. So when you are typing in a URL in your browser, like google.ca, your URL will send a request to a domain name server DNS and saying we have this string google.ca, please tell me which IP address I need to go to. And that's the idea. The domain name server will store a binary search tree that stores the keys as strings that are google.ca, ecg.utoronto.ca, and each of them has this value, which is IP address. And this is stored as an int, and this is what we are returning. Is this making sense? So your browser needs an IP address to send requests. But if you type in something like google.ca, your browser doesn't know which IP address to go to. So it will first go to domain name server to ask for the IP address. And your domain name server will store this as a binary search tree. It will look for google.ca inside the keys, and it will return the second value associated with that key, which is integer format as the IP address. So storing into this binary search tree is like this. We make a pair using the pairs constructor. The first element is a string. That's the domain name. And the second element is the IP address. We can insert that pair. Or option 2, we can use the STL library's make pair function. This will automatically determine the pair type for us, and it can be stored into auto type. Compiler will automatically determine the type for us. And we can insert that. Or option 3, we can directly insert the make pair object into the DNS lookup. So we can skip over the auto applet part. Is this making sense? So we're essentially storing pairs into the binary search tree. And we would strongly recommend option 3 because it's the most concise and you can do it in one line. So after we stored all of these, oh, and I forgot to mention we need to include the map container header. The map is a binary search tree that stores pairs. Now, can anyone tell me what should we use to search? So if we want to find something in this DNS lookup, what makes the most sense to be put into this bracket? The key or the value? How many of you would think this is the key? How many of you would think it's the value? It's the key. So the keys are the names that are stored in the strings. And the values are the IP addresses. So when your browser asks the domain name server, what is the IP address? It searches using the name, which is the key. So the browser has a name at apple.com and it asks for what is apple.com's IP address. And that's how it's done here. How do we check if the key was found? This .find function will return an iterator to wherever this key is stored. And the iterator is an iterator to the pair object. If it cannot find something, it will return iterator dnslookup.end. So if we want to check if the key was found, we just need to check whether the return iterator is dnslookup.end. If it is .end, then that means this domain name is not found. This key is not found. If it's not dnslookup.end, then it returns the iterator to that pair object, and you can dereference this iterator to get the first, which is the key, and the second, which is the value. Making sense? Confusing? This could be a bit confusing when you first hear it. Yeah, the iterator points to the entire node, which is an STD pair. And when we output it, we will see the name first and then the value, IP address. Now, exercise 2. Let's go on to that URL and go to exercise 2. So basically what we want is we want to use iterators and a for loop to print out all of the nodes in STD map. You can either use for loop and iterators, or you can use the range-based for loop. Anything you want. Anything that can go from beginning to end. You should be getting something like this. We go from beginning to end. We increment every time and we output first and then second. And if we're looking at iterators, we need to dereference. And this should be your output order. You should already be noticing that the output order is in ordered, ascending, ordered by the domain names. So we have Apple first, uToronto at the end. And this is because map is sorted, inherently sorted. And the map iterator advances as an in-order traversal of the binary search tree. In-order traversal means we're doing left, center, right. So we always have the smaller nodes on the left, center, and then the larger nodes on the right. That's in-order traversal, and in-order traversal of the binary search tree will be outputting a completely sorted output when we go from begin to the end. The other traversals are pre-order traversal, where center is at the beginning. So we do center, left, right, or the post-order traversal, where we're doing left, right, center. Just as a memory refresher for binary trees. So binary search tree, if we do in-order traversal, it's inherently sorted. MyMap.begin will point to the smallest element on the leftmost side, and MyMap.end will point to one past the rightmost node. Everything good? Give me some reactions, please. Good. And if we find, let's say, a value of 2, we will return the iterator to point to exactly that node. If we cannot find something, it will point to end. Now, let's consider what will happen if we have duplicate keys in the map. So in this example, we have a binary search tree that stores the salary database, and we are ordering that using the employee names as the key and the salary as the value. In this case, we have 2 John Smiths. What will happen for the binary search tree? At the second insertion of John Smith, the map will see that the key already exists, so it will ignore this line, and when we find it, we will only find the first John Smith. This is not what we want. We want to be able to cover all of the cases. So what to do? We would go to either one of these 2 websites and look in the containers library. Let me click on this one. C++references.com. And we go to the containers library. We should see there's the sequence containers, associative containers. We look inside the associative containers and we see there's the map. And there is something called the multi-map, which by its name should serve what we want to do. And let me zoom in. Multi-map is an associative container that contains a sorted list of key value pairs while permitting multiple entries with the same key. That's exactly what we're looking for. So that means we should be switching to multi-maps. So we switch from map to multi-map. Then with multi-map, if an insertion takes place, this will be successfully inserted. Now, but the find function will always only return one iterator to the first occurrence of this key. So that's not what we want. What we want to do is we go back to this website and we look for the member functions. It should be somewhere near the find for lookup. We see find is here, and then we look down and we see this description returns range of elements matching a specific key, equal range. That's the thing we need. And let's click on it and see. The return type is a pair of iterators, equal range, and the parameter it takes in is a key. That's how you look for it. And you should see the C++ versions here. And if we read through this, the range returns a range containing all elements with the given key in the container. The range is defined by two iterators, one pointing to the first element that is not less than the given key, and another pointing to the first element greater than the given key. Reading this, the first element that is not less than the given key means it could be equal to the given key or it could be larger than the given key. Another pointing to the first element greater than the given key. So there are two possibilities. One is the first element is equal to the given key, and you can query through this range because maps are inherently sorted, so you should be expecting it to be sorted. Another possibility is there is no match to the given key, and both of them will be pointing to the first element greater than the given key. So then we can use this equal range function, and the range returned from this equal range function, we can call a for loop here. We start from range.first. We check whether it's equal to range.second. If the range.first equals range.second, then we don't even need to enter this for loop. We just continue. If range.first is not equal to range.second, we can increment the iterator each iteration, and we can output it. Then in this case, John Smith earns 30,000, John Smith earns 45,000. So we can cover the entire range. What this returns? Visually, range.first pointing to the first occurrence of John Smith. If John Smith doesn't exist, first and second will both point to this one. If John Smith exists, it will point to the first occurrence of John Smith. Second will point to the first element that's greater than John Smith. So this one. So we will never be checking second. we loop from the first to 1 before second. Making sense? Those are two applications of binary search trees. We have other containers as well. So we have map, we have multi-map, we have unordered map. Unordered maps are not ordered. And you cannot sort an unordered map. Unordered map can never be ordered. But it has this really powerful find, insert, and erase complexities of O1. And I would expect unordered map to be the one type that is used most throughout your milestones. Our map is really useful when you don't need the elements to be ordered. A set is similar to a map, except sets do not have values. It only has keys. So if you only need keys, not their values, you can use the set. And there are other containers that are not maps or sets. Q is a 1D container that does first in, first out, bifold. Priority queue is a heap. So a heap is still a binary tree, but instead of the binary search tree where you have the middle one as the root of a heap is always either the largest by default or the smallest element. So when you push it, it's going to be O log n because you need to traverse through the tree, but when you pop it, you will always pop the root. And the root is either the largest or the smallest. There is one occasion where you'll need to use priority queue in this course. The stack is similar to queue, but instead of first in, first out, it's last in, first out, or first in, last out. A DQ is similar to a vector, but can be faster for insertions or deletions. The DQ is nearly never used in this course. So choose whichever container to use, matching your circumstance, not the other ones. So yeah. And these are probably two really useful structures. And from their name, one is ordered, one is unordered, but they are the two different structures. Map is a binary search tree. Unordered map is implemented by a hash table. Everyone knows what hash tables are. Hash tables allows really fast lookups and insertions and erases because they are essentially entries of this table, but nothing can be ordered in this case. And this is also a really good example of using iterators over indices because you can never index a hash table. You have to use indices to traverse through the entire order map. Good? Making sense? Course expectations, the STL is massive. We cannot teach everything to you, but it is very useful. So when you need to implement anything in ECE297, make sure you look up the most appropriate, the fastest container you can use in the STL. Demo 2. So this demo is just timing the map versus unordered map. So we remember the map complexity for insertion lookups are O log n. For on-order maps, everything's O1. So it's essentially a comparison between O log n and O1. Let me go to that folder. Just showing you I'm not cheating. These are the two source files. One with map, one with on-order map. Everything else is the same. We are filling them with some arbitrary values and we are searching randomly. Everything's the same except the first declaration. And because we are using iterators, we do not have to change anything other than the first declaration and probably the header. So we make clean first. And let me make in the release configuration. Let's time the map first. Remember, this is O log n. O log n should be fast enough. 0.57 seconds. Let's do the other one. 0.18 seconds. So both of them are less than 1 second. O1 is faster in all cases than O log n, but O log n is usually good enough. If it's not a really extensive performance test, you should be able to pass with O log n. But O1 is the safest and fastest you can get. That's our demo 2. And we can move on to our part C. Where is part C? STL algorithms. It's the last one we're covering today, and it's a quick one. So we've went through the iterators, we went through the containers, now the algorithm library. There is a function defined in the algorithm library for finding elements. It's a really common scenario. You have a collection of data, it's stored in some container. You need to find the specific value in the collection. In most of the containers, the find function is already defined for you. But there is another option defined in the algorithms library called stdfind that you can use. So yeah, there are more options than you would need to use. We're just showing you all of the options. So in order to use the find function in the STL algorithm library, the first thing is to include algorithm header. And then you can call the find function with the begin and end iterators for this collection. And then the last value is the value you're searching for, which is 3 in this case. Then the find function will return the iterator to the element that you're searching, or it will return the iterator to collection.end if the element is not there. Compiler will determine the type, but we should all know that this is an iterator, right? Then we check whether find is failed or it can't find that value using the comparison with a collection.end, everything should be familiar by this time. Keep this in mind and let's do our last exercise. So what we actually want here is we want to use std find and iterators. We want to make sure that the first element is 1 and only the first element is 1. So we want to do 2 comparisons. One is the first element is 1 or not. The other one is, are there ones in any of the other elements? If there is, then we return false. So we check if the first element is 1, then we check if the remaining elements for any are any ones. And we use the find function and iterators. This is under exercise 3. I don't think we have 6 minutes to do it, so let's do it quickly. And remember, the find function takes in 2 iterators, and you are free to change them. They don't necessarily need to start from begin and end. And quickly go over the rest. So this is essentially what we had before. Other examples from algorithm. We have the main function, we have the max function, we have the sort function, we have the find, we have the swap function, we have the count function that can count the number of elements with a given value inside a range given by a range of iterators. You can bring this exercise home if you want. So just find any function and try to answer these questions. Take sort as an example. You can go on to the website and you can go back to C++ and you can search for sort, std sort, and you'll be able to see that the simplest sort accepts 2 arguments that are random access iterators first and last. These 2 should have the same type. So the simplest one requires 2 both of the same types. What are the requirements placed on the arguments? They have to be random access iterators from what we just saw. How are the elements compared? And you can see in the first one, elements are sorted with respect to operator less than. So compared with operator less than. What is the complexity of std sort? Can anyone find this inside this page? Complexity. Given n as last minus first, O n log n. That's how you find all of the information you need for any of the functions that you'll be using. So sort will take in the beginning and end iterators, and it will take O n log n. Its preferred if you can comment in the complexities that you are not sure of, so you can still go back to it afterwards, and you can see in the comments what the complexity is. Then we can do a for loop and output the result from the sort, and you can see whether the operator less than will be sorting it into ascending or descending order and things like that. Okay, that's the last slide. Any question for me before we end today's tutorial? Okay, yeah, that's it for today's tutorial. Thank you for coming. We're just past 6, so I think we're